Double acting compressor operations and first law applications of thermodynamics. And this is a group presentation done by group 16. One may ask, what is a double acting compressor? A double acting compressor is a replicating compressor where the compression occurs on both sides of the piston in a single cycle. This design improves efficiency by doubling the compression work per revolution. Below is a detailed analysis, including case studies and diagrams. Operations of the double acting compressor. The main components are the cylinder, the piston, the inlet and outlet valves, the crankshaft and connecting rod, cooling systems. So below it we have the working principle: suction stroke, compression stroke, stimulus suction and compression stroke. We'll take the suction stroke, left side. The piston moves right side, creating a vacuum on the left side, allowing gas to enter through the suction valve. The compression stroke, left side. The piston moves left, compressing the gas and pushing it through the discharge valve. Stimulus suction, right side. As the left side compresses gas, the right side in the suction phase. Compression stroke, right side. The piston moves right again, compressing gas on the right side while the left side begins a new suction phase. This alternating processes ensures gas compression on both sides, improving efficiency. So this is the diagram we spoke about earlier in our previous slides, which is the piston, which we have the piston, the suction valve, the compressed gas, the cylinder, the inlet and outlets. Applying the first law of thermodynamics. The first law of thermodynamics states that energy can be transformed into one form into another, which is the change in internal energy equals the heat added minus the work done by the system. For a double acting compressor, work done on gas, gas is compressed, so work is done on the gas, where P1, V1 are initial pressure and volume, B2, V2 final pressure and volume, and N is the polytropic index, which varies between 1 for isothermal and gamma for adiabatic. The work done increases the pressure and temperature of the gas. Work done of the gas for eccentric compression where no heat is lost. We have our specific gas constant, the ratio of specific heat, the initial and final temperatures. Since compression occurs twice per cycle, the total work done per cycle is double that of a single acting compressor. Heat transfer. The compression process increases gas temperature, requiring a cooling system, either air or water cooled. Heat is removed from the system to maintain efficiency, preventing overheating and reducing energy losses. The amount of heat removed follows M, gas mass, CV, which is the specific heat at constant volume, T1, T2, which is the initial and final pressures. 3. We have internal energy change. Since the gas undergoes compression, its internal energy increases. The energy increase is related to temperature. If cooling is efficient, the internal energy rise is minimized. Thus, the first law of thermodynamics explains how energy is transferred as work done on the gas and heat removed through cooling. 3. Thermodynamic processes in a double acting compressor. Earlier we already explained what a double acting compressor is. So, a double acting compressor undergoes different thermodynamic processes. 1. We have the suction process, which is the isobaric expansion. Pressure inside the cylinder drops. Gas enters the chamber through the suction valve. Compression process. 2. Polytrop and eccentric trop. The piston compresses the gas, increasing pressure and temperature. Eccentropic. Idle gas. no heat loss, polytropic, real gas. Some heat loss occurs. Discharge process, constant pressure. The compressed gas exists The compressed gas exits through the discharge valve into storage or a pipeline. Efficiency. The efficiency of a double acting compressor depends on 1. Isentropic efficiency, which measures how much work input results in useful compression. 2. Volumetric efficiency, which is affected by the clearance volume and valve timing. Mechanical efficiency, which is reduced by friction and heat losses. Heat loss or also heat rejection. Heat removal is necessary to prevent overheating. Common cooling methods, water jets and air cooling. World applications of double acting compressors. Natural gas pipelines, refrigeration system, petrochemical plant and power plant. A case study, which is the industrial double acting compressor, which is used in the industrial world. An example is the natural gas compression application. It is used in oil and gas pipelines to maintain pressure. The problem is high energy consumption due to heat losses. The solution which can be done is the advanced cooling methods, which is the water cooled cylinders, which should increase efficiency by 15%. The outcome of this solution would improve fuel economy and reduce environmental impact. A summary of a double acting compressor. A double acting compressor compresses gas on both strokes of the piston. The first law of thermodynamics applies as energy is conserved via cooling through work done on the gas and heat loss. Efficiency is maximized through better cooling and reduced mechanical losses. These compressors are used in natural gas pipelines, refrigeration and industrial air compression. Thank you.